Look at that. A photon. A particle of light, racing through the void at, well, the speed of light. Massless, ephemeral, gone in an instant. But what if we could gather enough of them? Not hundreds, not millions. Enough that their combined energy warped space-time itself? For 7 decades, physicists have whispered about an impossible object. A black hole born not from the death of a star, but from pure light. No matter, no mass, just energy, collapsed under its own gravitational weight. They called it a Kugelblitz, German for ball lightning. And in 2024, we finally discovered whether this dream could ever become reality. In the next minutes, we're going to build a black hole from scratch. No stars required. We'll discover why Einstein's equations say it's possible, why quantum mechanics says it's not, and what that tells us about the fundamental nature of reality itself. Let's start with something familiar. Light. You're bathed in it right now. It bounces off every surface, carries information to your eyes, makes life itself possible. But here's what's strange. Light has no mass. Zero. It's pure energy, racing through space at 299,792,458 meters per second. A speed so fundamental, we literally defined the meter based on it. And yet, light can push things. Solar sails use light pressure to propel spacecraft. Laser tweezers can grab and move individual atoms. If light has no mass, how can it push? The answer lies in the most famous equation ever written. But we need to see it differently. Not as E equals mc squared, but as mass equals energy divided by c squared. Energy and mass are equivalent. They're the same thing, wearing different clothes. A photon has energy, and energy is mass, just expressed differently. Which means light does something extraordinary. It bends space-time. Every photon that passes through space creates a tiny gravitational dimple. Infinitesimal, unmeasurable, but real. And if one photon bends space-time just a little, what happens if we bring together enough photons to bend it a lot? (1955), Princeton University. A physicist named John Archibald Wheeler, the man who would later coined the term black hole, was thinking about light in a way no one had before. Wheeler asked a simple question. If mass creates black holes, and energy is equivalent to mass, could pure energy create a black hole? He published his answer in a paper called Geons, Gravitational Electromagnetic Entities. In it, he laid out the mathematical framework for what would become known as the Kugelblitz. The idea was elegant. Focus enough electromagnetic radiation, light, radio waves, X-rays, any photons, into a small enough region of space, and their combined energy would warp space-time so severely that they'd trap themselves. The light would form its own prison. No star needs to die. No matter needs to collide. Just light, collapsing under its own gravity. It sounds like science fiction. But Wheeler wasn't speculating. He was calculating. And his equations said it was possible. To form a black hole of any size, you need to compress enough energy inside its Schwarzschild radius. For a Kugelblitz, that means concentrating light into an impossibly small sphere. How small? A Kugelblitz with the mass of 2 Empire State Buildings would be smaller than a proton. That's taking 700 million kilograms and squeezing it into something 10,000 times smaller than a human hair. But here's the beautiful part. Wheeler's equations didn't care about the scale. They said Kugelblitzes could exist at any size. Microscopic ones, human-scale ones, even one the size of a star. For 70 years, this possibility has lived in the margins of physics papers. Theoretical, unbuilt, but never disproven. Until now. Before we get to why Kugelblitzes can't exist, we need to understand just how absurdly difficult it would be to even attempt building one. This is the National Ignition Facility in California, the most powerful laser system ever built. It can briefly generate 500 trillion watts of power. That's 1,000 times all the electrical generating capacity of the United States, for a few billionths of a second. Impressive, right? Well, to create even the tiniest Kugelblitz, one smaller than an atom, you'd need a laser 100 million trillion times more powerful. That's a 1 with 50 zeros after it. To put that in perspective, if the National Ignition Facility is a firefly, then a Kugelblitz-forming laser would be brighter than every star in the observable universe combined. And that's just for one the size of a subatomic particle. What about natural sources? The brightest things we've ever observed are quasars, supermassive black holes actively feeding on matter, shining with the light of 1 trillion suns. Even they don't produce anywhere near the intensity needed. The calculations show that even at the center of the brightest quasar ever observed, light is still about 1 billion times too weak to form a Kugelblitz. So, for 7 decades, the Kugelblitz remained theoretical, impossible to test, impossible to build. But according to Einstein's general relativity, possible. And that's where things stood, until a group of physicists asked a question no one had properly answered before. What happens when you add quantum mechanics? Because here's the thing. Wheeler's original calculation used classical general relativity, a universe of smooth spacetime and predictable paths. But our universe isn't classical. It's quantum. And in a quantum universe, empty space isn't empty at all. It seethes with virtual particles, popping in and out of existence too quickly to see. Most of the time, this quantum fuzz doesn't matter. But when you try to concentrate unimaginable amounts of energy into a space smaller than an atom, that quantum fuzz becomes everything. (2024). Eduardo Martín-Martínez, a professor at the University of Waterloo and the Perimeter Institute. José Polo-Gómez, a physicist working between Canada and Spain. Álvaro Álvarez-Domínguez at Madrid's Institute of Particle and Cosmos Physics. 3 physicists working across continents decided to do something that should have been done decades ago: include quantum mechanics in the Kugelblitz calculation. As Martín-Martínez later recalled, I raised some reservations that quantum effects may actually make it impossible to concentrate enough light. I was particularly concerned about the Schwinger effect. The Schwinger effect. Predicted in the 1950s by physicist Julian Schwinger, it describes something that sounds impossible: empty space giving birth to matter. When an electromagnetic field becomes strong enough, about 10 to the 18th power volts per meter, the vacuum itself becomes unstable. Photons can spontaneously split into pairs of particles, an electron and its antimatter twin, a positron. Light becoming matter. Pure energy crystallizing into mass. It's E equals mc squared running in reverse. Now, you might think, That's fascinating, but what does it have to do with Kugelblitzes? Everything. Because remember, to form a Kugelblitz, you need to concentrate enormous amounts of electromagnetic energy into a tiny region, which means creating electric fields far, far beyond the Schwinger limit. And when you cross that threshold, something beautiful and devastating happens. The light you're using to build your black hole starts turning into particles, electrons and positrons, matter and antimatter. And those particles, created inside your would-be Kugelblitz, are accelerated by the same intense electromagnetic fields to nearly the speed of light. And they escape, taking their energy with them. Imagine trying to fill a bathtub, but the moment the water level rises above a certain point, the tub springs leaks everywhere. The faster you pour water in, the more leaks appear. You can never fill it completely. That's what happens when you try to build a Kugelblitz. The more energy you add, the more particles are created. The more energy escapes. You're fighting against quantum mechanics itself. What Polo-Gómez, Martín-Martínez, and Álvarez-Domínguez did next was extraordinarily difficult. They had to calculate two competing rates. On one side, how fast can you pour electromagnetic energy into a region of space? On the other, how fast does the Schwinger effect drain energy away through particle creation? The math was brutal. They couldn't use standard approximations. The feedback was too complex. Particles creating fields, fields creating more particles, everything interacting at once. Between Blackboard sessions and transatlantic video calls, they worked out analytical solutions to the differential equations governing energy dissipation. And when they finally had their answer, they found that the Schwinger effect always wins. For Kugelblitzes ranging in size from 10 to the -29th meters, near the Planck length, the smallest meaningful distance in physics, all the way up to 100 million meters, about the distance from Earth to the Moon during a close approach. Quantum mechanics drains energy faster than you can add it. The Kugelblitz never forms. The event horizon never closes. The dream dies before birth. Their paper was published in Physical Review Letters in July 2024. The title says it all. No black holes from light. But here's what's remarkable. They didn't just prove Kugelblitzes are impossible in laboratories. They proved they're impossible anywhere in our universe. Not in supernova cores, not at the centers of quasars, not in the collision of neutron stars. Nowhere in nature does light concentrate intensely enough to overcome the Schwinger effect. In all of cosmic history, under all known physical processes, a Kugelblitz has never formed. Never. But let's rewind. All the way back. Past galaxies forming, past the first stars, past the cosmic dark ages, past the time when atoms first formed. Back to the first trillionth of a second after the Big Bang. This epoch is called inflation, a period when space-time itself expanded faster than light, stretching quantum fluctuations to cosmic scales. In this primordial chaos, the rules were different. Space-time was already curved, wildly curved, by the expansion itself. And in those pre-existing curvatures, electromagnetic energy might have been able to collapse before the Schwinger effect could drain it away. For perhaps a tiny fraction of a second, when our universe was writing its own rules, Kugelblitzes might have briefly existed. And if they did, some physicists speculated they could account for dark matter, the invisible substance that makes up 85% of the universe's mass. But here's the truth. We don't know. The 2024 paper leaves that possibility open, but it's speculative. The conditions during inflation were so extreme that our equations might not even apply. What we do know is that in the universe as it exists now, in every galaxy, every star system, every moment since inflation ended, Kugelblitzes are impossible. And maybe that's okay. This story isn't really about Kugelblitzes. It's about something deeper. It's about how the universe protects itself. Einstein's general relativity tells us how mass and energy curve space-time. It's breathtakingly beautiful and accurate. It predicted black holes decades before we found them. It told us the universe is expanding. It showed us how gravity bends light. But general relativity treats the universe as smooth, continuous, classical. A universe where you can, in principle, focus infinite energy into a point. Quantum mechanics says, not so fast. At the smallest scales, space-time isn't smooth. It froths and seethes with quantum uncertainty. Particles appear and disappear. Energy fluctuates wildly. Nothing is perfectly precise. For a century, physicists have tried to reconcile these two great theories. In most situations, you can use one or the other. Gravity problems, general relativity. Atomic physics, quantum mechanics. They each reign in their own domain. But at extremes, inside black holes, during the Big Bang, at the collision point of particles in accelerators, the two domains collide. And we don't fully know how to handle it. The Kugelblitz calculation is one of the first times someone has successfully brought quantum field theory and general relativity together to answer a concrete question. And the answer they found reveals something profound. Quantum mechanics doesn't just tweak general relativity's predictions, it vetoes them. It says, you cannot concentrate energy infinitely. The universe won't allow it. The vacuum itself, empty space, has structure, properties, limits. It's not a passive stage where events unfold, it's an active participant, enforcing constraints through quantum effects. Empty space is like water. Pour a little energy in, and it barely ripples. But try to pour too much too fast, and the water pushes back. Let's talk about how this discovery happened. Not just what they found, but how they found it. 3 physicists, 2 countries, thousands of kilometers apart, working together across time zones, sharing blackboards through screens, arguing over equations, checking each other's work. And here's what struck me. This wasn't a billion-dollar experiment. No particle accelerators, no space telescopes, no satellites. Just mathematics. Pencil and paper, or more accurately, computers and video calls. They used differential equations that have existed for decades. Quantum field theory developed in the 1940s and 50s. General relativity from 1915. The Schwinger effect, predicted in 1951. All the pieces were there. What they did was put them together in exactly the right way to answer a question that had lingered for 70 years. And they didn't just answer it, they settled it. The debate is over. Kugelblitzes don't exist. Their paper has been covered in Nature, Physical Review, Live Science, across the physics community. Not because it's controversial, because it's definitive. And here's what I love about this. They didn't prove something we wanted to be true. They proved something we might have wished wasn't true. Kugelblitzes would have been incredible. Black holes from pure light, mini laboratories to study quantum gravity, potential power sources for future civilizations. Some physicists had even speculated they could power starships. The ultimate engine, a black hole in your basement, fed by lasers, with Hawking radiation providing thrust. None of that is possible. The dream had to die. And yet, this is science at its best. Science isn't about defending the ideas we love. It's about finding the truth, even when truth says no. It's about being brave enough to prove your own dreams wrong, and wise enough to see beauty in the answer. So Kugelblitzes don't exist. But here's what we did gain. First, the Schwinger effect, this quantum process where light becomes matter, has been verified. The calculations show it requires only about 1,000 times more energy than our most powerful lasers can produce. That means, within our lifetimes, we might actually observe it directly in laboratories. We might watch in real time as photons split into electrons and positrons. We'll see creation itself. Second, we now know that quantum effects can successfully be integrated into gravitational calculations. This paper is a proof of concept. If we can do it for Kugelblitzes, we can do it for other extreme scenarios. Black hole evaporation, wormhole stability, the earliest moments of the Big Bang. All of these require understanding how quantum mechanics and gravity interact. And this paper shows we can do that calculation. Third, the same mathematics that killed the Kugelblitz might open other doors. Martín-Martínez's group is now exploring whether quantum effects could enable other exotic phenomena. Negative energy, warp drives, traversable wormholes. Now, let's be clear. We're not building warp drives tomorrow. But we are learning which science fiction dreams might be real and which are impossible. And understanding why makes us smarter. Let's zoom out. Way out. Because there's a bigger picture here, and it's worth savoring. We are tiny. Our planet is a mote of dust in a sunbeam. Our civilization has existed for the blink of a cosmic eye. Everything we've ever built, every person we've ever loved, every idea we've ever had, occupies an infinitesimal fraction of space and time. And yet, these tiny creatures, on this tiny world in this tiny moment, have figured out why Kugelblitzes can't exist. Anywhere. Ever. In the entire observable universe. Think about what that means. We've never been to a quasar. We'll never visit the center of a black hole. We can't rewind time to the first second of the Big Bang. And yet, through mathematics, through the power of understanding patterns, logic, and the laws that govern reality, we can know what happens there. We can sit in a room, work out the math, and make statements about the entire universe that are true. Not guesses, not opinions. True. This is humanity's superpower. Not strength, not speed. The ability to understand. To look at the universe and see not just what it is, but why it is that way. The universe doesn't hand us answers. It's indifferent to our existence. But hidden in its behavior are patterns, laws, regularities, mathematics. And we've learned how to decode them. Every equation we solve is an act of defiance against cosmic indifference. Every discovery is proof that understanding is possible, that truth is accessible. And here's the most beautiful part. This knowledge isn't locked away. Anyone can learn it. The equations that describe the Schwinger effect are available in textbooks. The paper disproving Kugelblitzes is freely accessible online. The universe's secrets belong to anyone curious enough to seek them. So let's return to where we started. A Kugelblitz will never exist in our universe. Not in labs, not in nature. Quantum mechanics forbids it. Does that make the universe smaller? Diminished somehow? No. It makes it more remarkable. Because look at what does exist. Black holes formed from collapsing stars. Supermassive black holes that anchor galaxies. Binary black holes that merge, sending gravitational ripples across space-time that we can detect from Earth. These aren't hypothetical. They're real. We've seen them. We've heard them. And beyond black holes, neutron stars that pack the mass of the sun into a sphere the size of a city. Pulsars that sweep radio beams across space like cosmic lighthouses. Magnetars with magnetic fields 1 billion times stronger than any human technology. The universe doesn't need Kugelblitzes to be astonishing. Reality, actual, verified reality, is sufficient. And we're still at the beginning. We don't know what dark matter is. We don't know what dark energy is. We don't know if our universe is one among many. We don't know how quantum mechanics and gravity truly unify. The Kugelblitz was a beautiful idea. For 70 years it lived in the dreams of physicists, a ghost at the edge of possibility. And now, thanks to 3 people with paper and equations and determination, we know it was only ever a ghost. But here's what I want you to remember. Proving something is impossible isn't a failure, it's a triumph. Because knowing what can't happen tells us what can. Every boundary we discover makes the map more accurate. Every constraint we find makes our understanding more precise. Every dream we prove wrong makes the dreams that remain more precious. The universe has rules. Deep, mathematical rules. They limit what's possible, yes, but they also make everything that is possible, possible. If quantum mechanics didn't exist, if the Schwinger effect didn't drain energy away, if Kugelblitzes could form, the universe would be a different place. Maybe an unstable place. Maybe a place where concentrated energy collapsed uncontrollably. Maybe the very fact that we're here, that stable matter exists, that atoms endure, that life could emerge, depends on Kugelblitzes being impossible. Sometimes the universe says no, because it's already said yes to something better. That photon is still traveling, massless, ephemeral, free. It will never collapse into a Kugelblitz. It will never trap itself. Instead, it will travel for billions of years across empty space, until finally, perhaps, it meets something remarkable. A retina, a telescope mirror, a sensor. And in that meeting, that tiny quantum of light will become something even more extraordinary than a black hole. It will become knowledge. The universe is knowable, and we are the ones learning to know it. This is Cosmic Canvas, where light travels freely, never collapsing, only illuminating. Until next time, remember that the universe didn't need a Kugelblitz. It only needed you to notice the photon.